What's going on? Okay, let's try it again. What's going on, guys? I actually did a few lectures before this, so I have chalk all over the place right now. But yeah, this is the second installment. I believe I only did one before of the Q&A for Math 1206 Spring 2020. As you guys all know by now, the coronavirus pandemic has hit New York. It's hitting us pretty hard. I think we're pretty much the worst one at the moment. We are the state with the most number of cases. It's really giving us a hard time. But we will survive. We will get through it. That being said, for most of my other classes, I am just continuing live video recordings and posting them and following up afterwards. But for you guys, since I actually wasn't recording any lectures for you guys, I just referred you to lectures I previously recorded, and I would have done exactly the same examples. Calculus hasn't changed in the past 300 years. I'm not going to change what I did last semester or the semester before that. So you guys have been watching the lectures, keeping up with those guys and asking me questions on anything that is off to you from those lectures. So I would answer the question in a Q&A session like this one. Right now, as of today, or technically as of last night, you should have been up to lecture 23 in the playlist that I will link in the video description. And so I'm answering questions on that. Let me grab them for you. So it turns out that I only have 2 questions to answer. So I had some people reach out to me and just to let me know that, hey, I watched the lecture 23 and I didn't really have questions. I think everything was good, and that's all fine with me. Just make sure that you know that's true for sure. Here's one thing that I really worry about happening to you guys is that sometimes if you just sit down and watch the lecture, it would feel like everything, oh yeah, that makes total sense and I totally get everything. It's actually a very different experience if, while watching the lecture, before I do examples or anything like that, you would pause the video and try the examples yourself before I actually do them. You'll tend to find out the lecture wasn't as easy as you thought it is. So hindsight is 2020. This is very true in math class. It is a very common thing that will happen to math students, that they feel blindsided by a math test. They actually, a lot of them feel like the math test was different from what happens in class, which is rarely true in math class. Actually, yeah, it's one of these jokes that everyone thinks, oh, on the test, he just asked us about Pythagoras', in the class we did Pythagoras' theorem, and on the test he asked us to calculate the mass of the sun, or, you know the memes. It's very rare in math class, actually, but I know there are classes like that, but it's rare in math class, super rare in a calculus class. What you do in class is going to be exactly what's on a test. If you have a lot of trouble in the test, but you feel like you're understanding what's going on in the class, then the culprit is you're just watching the class and just watching me do everything, and you're not actually trying things on your own. You'll realize that if you were to pause the video and try the problems on your own, it's probably not as straightforward as you thought it was. Watching something is going to be obvious after I do it, but if I didn't show you how to do it, it's not as obvious somehow. So keep that in mind. Be sure that you don't just have my lectures running in the background, or you're doing it while you're washing the dishes, you have the lecture running or whatever. No, please take an active learning approach. It's more important now that we are doing this long distance learning thing. It's more important now than ever. You don't have the interaction, that feedback. You're not in a classroom setting where you can't just do whatever you want, and you can't just, well, you can technically pay attention, but it's harder to do it in class as opposed to you're at home lying in your bed, playing with a game on your phone while watching it. It's a completely different atmosphere, and that actually can make it a lot worse for you. So be careful. Make sure that when you're watching the videos, you take an active, engaged learning approach. Set aside the time when you're watching the lecture just as you would if you were sitting in class and you couldn't do anything else. Pause the video, try examples before I do them, especially if I throw out a question to the class, because I do that, like when there are students around. What do you guys think about blah, blah, blah? Make sure to pause the video whenever I ask a question like that and try to answer it yourself. Then start the video again and see if the answer that we came up with was the answer that you came up with. That's going to be very important. So I had a couple people reach out to me saying that they get it, they didn't have any questions, we watched the video, just letting you know everything was clear. And all power to you, I'm happy to hear that. I just want to make sure that that is actually true and you're not fooling yourself, which that's not something to knock against the students who said they understand, because it happens to the best of us. We can watch something, we can watch someone do something, and it seems, oh yeah, that seems easy, that looks like it makes a lot of sense, but to do it yourself, it's a completely different story. So make sure you're not falling into that trap. That being said, let's move on to the questions. I have a question from a student, and like I said, I'm not going to identify anyone unless they tell me it's okay. So this is referring to, I believe this question actually came from lecture 22. So the question is, I mostly understood the lecture, but one thing that was kind of iffy about was how the squeeze theorem was used to prove Fermat's theorem. It says how the squeeze theorem proves Fermat's theorem. We didn't really prove this Fermat's theorem from the squeeze theorem, we just used the squeeze theorem at a certain point. This was done in lecture 22 though, but I can talk about it. First of all, what I would say is I would never actually ask you to do the proof of Fermat's theorem. It's not something I'm going to ask you about. There are not many proofs that I would ask you about in a Calc 1 class. So the things that you can be expected to prove are things using like the intermediate value theorem, or things using like Rolle's theorem or the mean value theorem, or not proof of the mean value theorem, using the mean value theorem to prove like you attain the mean slope somewhere. What else? The epsilon delta definition of a limit. So yeah, things like that. So proofs that I would ask you to do are kind of proofs that are problem solving kind of proofs. You prove the answer to some specific problem that I'm talking about. Those are proofs that I would ask you. So I won't ask you to prove like a general theorem, like Fermat's theorem or anything like that. That being said, they asked the question, so I'm going to answer it. Fermat's theorem was the theorem that said if f attains a max or min at x equals a, and f prime of a exists, then f prime of a must have been 0. Or I believe I use c, or something like that. X equals c. I believe I use c, so let's make it look the same. Now, we know that the converse of this is not true. It's possible for the derivative to be 0 and you not have a max or min. It's also possible to have a max or min when your derivative does not exist. However, if you have a max or min and you know the derivative exists at that point, then the derivative must be 0. Now, I'm not going to go over the entire proof at this point, but I want to show what we did in the proof. We showed two things. We showed that f prime of c was greater than or equal to 0 in one situation, and we showed that f prime of c was less than or equal to 0 in another situation. And we did this by finding the limit. We did this by finding the limit as h approaches 0 of f of c plus h minus f of c all over h. So there came a point where we had the expression f of c plus h minus f of c all over h. We showed that that was less than or equal to 0 at some point. Then we did an approach from the other direction, and we showed that that was greater than or equal to 0 at some point. And basically what we did was, at this point, we took the limit of everybody. So these outer parts gave you 0. This part is, of course, f prime. And this part is, of course, 0, which is what we ended up proving one side at a time. But ultimately, if you consider both of these together, you get one long three-way inequality, where we can apply the squeeze theorem to that. So this fact told us that f prime of c equals 0 by the squeeze theorem. That's because we have this limit squeezed between two limits that both approach 0. So I think in the proof I did it one side at a time, so you probably didn't realize that was what was going on. But if you look at both sides in one big inequality, then because both sides would go to 0, the squeeze theorem tells you that the middle one must go to 0. So look up what the squeeze theorem says, and that will help you. So I don't know if I want to spend time writing this down, but let's just do it since I'm here. So the squeeze theorem is the guy that says if f of x is between h of x and g of x, and the limit of as a approaches this equals L, and the limit as x approaches a of g is L, then the limit as x approaches a of f must be L, right? So this is provided all of the limits exist. So as long as we can take a limit, this is true. So the idea is I can take the limit of all sides, limit, limit, limit. If the two outer ones go to the same number, it squeezes the middle one in between the same number. It has to be that number. The only way you can be less than or equal to 0 and greater than or equal to 0 at the same time is for you to be 0. So you get squeezed in between the two numbers on this side. So that's how the squeeze theorem actually applied to Fermat's theorem. There came a point where we applied the squeeze theorem to finally conclude that f prime of c must be 0, because we know it's both greater than or equal to 0 and less than or equal to 0 at the same time. So rewatch the proof for that, see if you get it. However, in general, I wouldn't sweat it too much unless you want to go a lot further in math. You're going to be a math major, you're going to be a physicist or something like that. And maybe, depending on if you want to go into engineering, how much you want to understand, you might want to pay attention to things like that. But I'm not going to test you on the proof of Fermat's theorem in general. However, there are times where I'll test you on the squeeze theorem. In fact, on test 1, I tested you guys on the squeeze theorem. Yeah, so it's good that you asked that question. Technically, you don't really need to know it for this class because I'm not going to test you on it. But hey, if you're interested, that's good. And if you're going to be a math major or something like that, as I said, you should be interested. If you're not interested, you should probably question your major at that point. I have another question. Again, not going to say who it's from, but it is from lecture 23. When you're doing example 2b, how did you know to stop at 7 pi over 6 and 11 pi over 6 as opposed to 8 pi over 6 or 10 pi over 6? So I had to look up the lecture. And I should mention here, thank you very much for your question, but to make things a little bit nicer and quicker for me to get through the questions, please give me the timestamps when you want to ask a question. So don't just say example 2b, because now I have to look through the entire lecture for when I did an example 2b. And that just makes things a little bit harder. And I don't have many questions this time around, which is why it wasn't a big deal. But if I had like a bunch of people ask me a question on a particularly confusing lecture, then having the timestamps to be able to jump to is going to be very helpful. So just to remind you of the example that we're talking about here, we wanted to find the absolute max and min of f of x equals 2 sine x minus cosine 2x on 0 to 2 pi. Now, what we had to do here was to apply the closed interval method. So the closed interval method said if you have a continuous function on a closed interval, You can find the absolute max and min by the closed interval method. It has 3 steps. So the first step is to find all critical points in the interval, evaluate your function at those critical points. Then you want to evaluate your function at the endpoints, namely plug in 0 into this function and plug in 2 pi into that function and find the y values there. And lastly, you're going to compare all the y values. The biggest one is going to be your absolute max, the smallest one is your absolute min. Now, we know, by the way, parenthetical statement, we know that a continuous function on a closed interval will attain an absolute max and an absolute min because of the extreme value theorem. So, that being said, at one point we had to, let's just quickly run through a little bit of this. I mean, it's the last question we have for today, actually, so I can spend a little bit of time on it. So step 1 was to find the critical points. Critical points is where f prime is 0 or undefined. So I'm going to go through, I'm going to find f prime. Becomes plus, right, because I applied the chain rule here. The derivative of cosine is minus sine, then I have to multiply by derivative of 2x, which is that, and derivative of sine x is cosine x. So that's your derivative. You set equal to 0 or undefined. This is for critical points. Now, this is never undefined. It's a function of sine and cosine. So we only cared about where that was 0. This guy was sine 2x is 2 sine x cosine x. So this ends up being 4 sine x cosine x equals 0. I can divide both sides by 2. I get cosine x, or I can factor out 2 cosine x. I would be left with 1 plus 2 sine x equals 0. So I get cosine x equals 0, or or 1 plus 2 sine x equals 0. Now, cosine equals 0, we only care about where cosine hits 0 between 0 and 2 pi. By knowing the graph of cosine, you will know that this will happen at minus pi over 2. We're between 0 and pi. It's going to happen at pi over 2 and 3 pi over 2. Cosine of x equals 0, so this means that x equals pi over 2 and x equals 3 pi over 2. And you would know that from the graph. Right, so the graph of cosine looks like this. That's at pi over 2, that's at 3 pi over 2. Right, which you should know. That's what it looks like between 0 and 2 pi. And for the part with 1 plus 2 sine x, this means that our sine of x is equal to minus 1/2. And this is where the question is coming in. So I'm not going to complete the problem because you can go and finish watching lecture 23 to see the full solution. This is just in step 1 is where the question came from. And so now we have to solve this. Now, how you go about solving where sine of x equals minus 1/2? Well, you would use reference angles. To find where sine x equals minus 1/2, solve sine x equals positive 1/2, which you know from that table. I actually drew it in the lecture. This happens the first place at pi over 6. So we have our unit circle here. Pi over 6 means you divide into 6 pieces. And pi over 6 is the angle here, pi over 6. That's where your sine hits positive 1/2. Now you know from all students take calculus, all students take calculus, that the sine will give you a positive answer in the first and second quadrant. So the answer to get the negative signs, the negative part here, this tells you you need to be in Q3 or Q4. So you want to find the angles that are in Q3 and Q4. Namely, what you want to know is the reference angles. Now the reference angles are the angles that are closest to the x-axis. And therein lies the answer to your question. So, that would be pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6 are the guys we care about. Now the question was, why did we stop at 7 pi over 6 and 11 pi over 6 as opposed to 8 pi over 6 and 10 pi over 6? The reason is 8 pi over 6 and 10 pi over 6, these guys are not reference angles. You won't use them to evaluate the sign where a sign hits either a plus or a minus a half. You would use reference angles. Reference angles are the guys that are closest to the x-axis. This is farther away from the x-axis than that guy. That's why I choose this guy instead of that guy. Similarly, this is closer to the x-axis than 10 pi over 6. That's why this guy is chosen. When you want to figure out the value of the trig functions in the different quadrants, you use the idea of reference angles to figure them out. Once you know about how things behave in the first quadrant, you'll automatically know how things behave in the second quadrant with the help of all students take calculus and reference angles. So that question is a question that is answered by reference angles. Now, to review, which you should be reviewing, since now you have time, right? Watch my Math 1000 lectures. I believe it's also, as fate would have it, lecture 23. In lecture 23, I talk about reference angles and their use in actually solving trig equations. In fact, in Math 1000, the last few lectures, lectures 21 through 26 or something like that, is me telling you a lot of trig. And that was for a pre-calc class, but it's actually super important, not only in calculus, but in calculus 2. You're going to need to know a lot of trig for calculus 2 in general. Depends on how it's being taught. But yeah, so I choose 7 pi over 6 and 11 pi over 6 because they are reference angles for pi over 6. 8 pi over 6 and 10 pi over 6 are not. And so that's why you would choose them. You always choose the guys that are closest to the x-axis. So that's the question there. And we're just a little bit over 20 minutes in. Nothing else to really answer here. That other question is from another class. So yeah, hopefully that was helpful. So we use the squeeze theorem in Fermat's last theorem because there came a point where the derivative was both greater than or equal to and less than or equal to 0. So that's where that came in. And I chose these angles instead of those angles because those guys are reference angles. So that's how I would know. So the x that causes sine x to be minus a half that fall between 0 and 2 pi are 7 pi over 6 and 11 pi over 6. You can watch the lecture 23, or you should have watched lecture 23 for the full solution. That being said, I hope you're all well, and I believe this question, yeah, came from someone in my class who had a mock quiz today. The first question came from someone who will be having their mock quiz on Friday, which I still have to worry about. So yeah, I still have to tell you guys about testing and all that good stuff. But like I said in an email, quizzes are postponed. I'm really just posting mock quizzes at the moment, so they're not going to be graded officially, but they're just going to make sure that you're keeping up with your studies, a way for you to test yourself. So I'll post a quiz. Actually try to do it on your own, because that way how you perform is going to be indicative of what you understand. And it's not, there's no downside to it, right? So you're not going to be downgraded if you do bad on one of these mock quizzes. It's really for your own benefit to know where you stand. So take those guys seriously. Keep watching the lectures. Keep sending questions my way. Also, depending on when you see this, I will have my office hours as usual on Wednesdays and Fridays by Zoom. So if you were to contact me at any point now, I would be able to send you a link, but I'll actually send a general Zoom link to the class for you guys to actually see me during office hours. That being said, have a good night, stay safe out there, and ciao.